which, if it were true, would explain what they're finding. So you may have heard of this. They said that this thing was the proof of what they call the wave-particle duality of light. So sometimes light behaves like a wave, sometimes it behaves like a particle. What makes the difference? Well, you may have heard of this too. If you observe light as if it was a particle, it behaves like a particle. If you observe light as if it was a wave, it behaves like a wave. So the next thing in quantum physics, which you might have heard of, is the observer effect, which basically says, depending on the way that you observe light, the light will change. So if you observe it as if it's a particle, it behaves like a particle. If you observe it as if it was a wave, it behaves like a wave. Now this completely blows out the existing thinking of physics at that point in time, Newtonian physics, which was that the observer was completely separate from what was observed. What we've got here is that when you observe something, you change its very nature. Now, here's another little experiment they did. They took away the light bulb and they pointed a telescope at a distant star. Let's say this star is 100 light years away. So the light took 100 years to get from the star to here. And they took the light from the star and they put it into this experiment. When they closed that slit there, the light from the star acted like a particle. When they opened that slit there, the light from that star acted like a wave. But the light left the star 100 years before the experiment. Does that mean, this is another rhetorical question by the way, does that mean the act of observing something right now changes 100 years history? It's because you're changing the nature of the light right now, but the light left and was created by the star 100 years ago. So this experiment created the wave-particle duality of light and the observer effect. But let's just talk a little bit more about the observer effect. Because the observer effect is pretty mind-blowing. In fact, there was a quantum physicist, and one of the things he said was, if when you read about quantum physics, you aren't absolutely appalled by the repercussions of what quantum physics is saying, you don't understand it yet. Because what quantum physics is actually saying is totally mind-blowing as far as the structure of our universe and the structure of our reality. So they did an experiment. Now, this actually, I'll tell you now, before I tell you about the experiment, this experiment wasn't a real experiment. It was just an experiment that people did in their minds. Okay? And it was an experiment by a guy called Schrödinger. He said, if we take a box, like this, and we put a cat in the box, now you're going to realize why I'm an NLP trainer, not an artist. Because that's actually a cat. Actually, that's a Manx cat. It's a tail. Now you can recognize it. Oh, now you put the tail on, David. I know what it is. So there's a cat, a live cat in the box. And what they said was, let's put some deadly poison in the box with the cat. And let's put a special device onto this bottle of deadly poison. And this is why I said this experiment wasn't actually done. There were no animals harmed during this experiment. It was just postulated in somebody's mind. And they put a special device on this, which meant in a certain period of time, there was a 50% chance that the poison was going to be released and it would kill the cat. And a 50% chance the poison wouldn't be released and it wouldn't kill the cat. Yeah. And then the box is closed. And you can't see inside the box. Now, after that certain period of time, whilst the box is closed, the cat is in a rather unusual state of being because it can't be dead and it can't be alive. There's just a 50% chance it's alive and there's a 50% chance it's dead. Which means, until somebody opens the box and checks, the cat is in this rather unnatural state of being half dead, half alive. But it can't be either of them. It's kind of both of them, both at the same time. So let's say that curiosity gets the better of me, and I open the box and have a look. And the cat's still alive. But I don't tell you guys. So now I have a universe with a box with a live cat in it. Everybody else in the room has a universe with a box with a cat in it, which is 50% alive and 50% dead. So my universe is now different than yours. With me so far? Now let's say Leon, curiosity gets the better of Leon here. And Leon opens the box, has a look, and the poison's been released, and the cat's dead. But he doesn't tell anybody else. So now I have a universe with a box with a live cat in it. Leon has a universe with a box with a dead cat in it. And the rest of you have a universe with a box with a cat which is in this strange state of being 50% alive and 50% dead. So in actual fact, we have different universes. But what changed my universe and what changed Leon's universe to be different from yours? Observing what was in the box. Until you look at what's in the box, it doesn't change. I think this is actually, until Leon's curiosity got the better of him, the cat couldn't be dead in this universe. I think that's where the saying, curiosity killed the cat, comes from. Because until you get curious and have a look inside the box, it can't be dead. It's 50% alive and 50% dead. So the actual act of observing freezes the cat into one particular state of being. And until you observe it, you just have probabilities. Yeah? So this appears to be the way that the universe is constructed. What you've got, it's almost like, have you heard of the story of King Midas? King Midas thought that everything in the entire universe was made of gold. Because as soon as he touched it, it turned to gold. And you're a bit like King Midas is, because you're walking along the road, and what's behind you is just complete chaos. What's behind you is everything that possibly could be behind you is behind you, all at the same time. All at different levels of probability. Some more probable than others, but it's all there. Just pure chaos behind you. And you keep attempting to catch it out and find out what that looks like. But as soon as you turn around and look at it, you observe it, and you freeze one particular probability. And you know that observing it changed it. The thing is, you don't know what it was like before you observed it. All you can say is, once I observed it, it was like this. Before I observed it, all we have is probabilities. Till we observe the cat, we've got a probability of 50% is alive, 50% is dead. Once you observe it, it becomes 100% one or the other. But until you observe it, it's in this strange probability state. And that's what the entire universe is like. So, another experiment. And what they did was they took an atomic particle, I'm going to say it was an electron, it wasn't actually an electron, but let's just say it was an electron. And they fired another high energy particle at it. And two other particles fly off. Let's say they're electrons again, but they're not. But what they did was they measured the direction this electron was going in. Now, as soon as you observe the electron, its direction changes. So all you can say is, after we observed it, its direction was this, but we don't know what direction it was going in before we observed it. With it? Because observing it changed it, and we don't know where it was before. Now, the weird thing is, that's the observer effect, the weird thing is, what they found was, if this electron changed direction like this, as soon as you observed it, they found that this electron here changed in exactly the same time, in exactly the same way, at exactly the same time. So when this one changed, that one changed in exactly the same way. There was no time delay between the two changing.